We're about to explore how scientists are peering inside solid objects and how AI is on the verge of giving them what you could almost call superpowers.
Here's what we're covering. First, the big problem, seeing inside things that are completely sealed off. Then, we'll get into a really clever technique called particle tracking. From there, we'll see the push to make it even more precise and how AI is the secret ingredient making it all happen. And finally, we'll look at what this means for the future.
Let's jump right in by tackling a core challenge in both science and engineering, and that's the problem of seeing the unseen.
How do you see what's happening inside a sealed metal engine or a chemical reactor? These critical processes are happening inside thick, solid steel. You can't just point a camera in there and watch the fluids move. This black box problem is a massive hurdle for anyone trying to improve these systems. High-speed cameras are amazing, for sure, but they have some serious limitations. They need to see through something clear, and you always have this trade-off. Get a really detailed view of a tiny area or a big-picture view that loses the fine details. But this is where a technique called PEPT, or Positron Emission Particle Tracking, completely changes the game. It works inside solid, opaque materials, gives you full 3D tracking across huge spaces, and doesn't sacrifice that high resolution.
So how does PEPT actually let us see the invisible? It all comes down to a really clever use of nuclear physics.
The real genius of PEPT is its simplicity. Instead of trying to capture a picture of everything at once, it just follows one single tiny radioactive particle. By tracking that one tracer, it can map out the dynamic flow of a system. Think of it like figuring out a city's traffic flow just by following one single car. Here's how it works, broken down into 4 steps. First, a radioactive tracer emits something called a positron. Almost instantly, that positron bumps into a nearby electron and they annihilate each other. This annihilation creates 2 gamma rays that shoot off in perfectly opposite directions. A scanner then detects both of those gamma rays. The path between those 2 detection points forms what's called a line of response, and somewhere along that line is our particle.
And the real magic here? It's those gamma rays. They have enough energy to punch through about 50 millimeters of solid stainless steel. That's almost 2 inches. This is exactly why PEPT can see deep inside industrial machinery that's completely opaque to any kind of camera.
PEPT is already an incredibly powerful tool, but the next frontier is about pushing its precision to a whole new level. We're talking about going from the scale of millimeters all the way down to microns.
Right now, the technology is stunning. We can pinpoint a particle's location to within a fraction of a millimeter, and we can do it thousands of times every second. That gives us an amazingly detailed picture of even the most complex movements.
And making PEPT better isn't just about getting a sharper image. As this quote explains, a breakthrough in how we measure things can set off a chain reaction. It drives new theories, better computer simulations, and even smarter equipment design. Put simply, better tools lead to better science across the board.
How do we make that leap? The answer, it turns out, is artificial intelligence. It's the key that's unlocking this next level of precision.
The big innovation is applying deep learning models to the problem. The AI isn't replacing the physical scanner. Instead, it's being trained to take the raw, messy data that comes from the detectors and clean it up, refining it, cutting out the noise, and dramatically boosting the final resolution.
But how do you teach an AI to do this? You run into a problem. With real-world data, you never know the particle's exact location. There's no perfect answer key. The solution is you train the AI on simulated data. Using computer models, you can generate mountains of perfect, noise-free data where the particle's location, the ground truth, is known with absolute certainty. The AI learns the ropes in this perfect digital world before it's ever let loose on the messy, unpredictable data from the real world.
The AI has 4 main jobs, which together amount to a total digital cleanup of the signal. It has to filter the data, pinpoint the location, refine the details, and then remove any remaining interference.
First up, the AI has to figure out which signals are legit. The detector picks up all sorts of stuff, and not all of it is a real event. The AI's first job is to act like a filter, learning to tell the true signals apart from all the random noise and false positives.
Once it has a signal it trusts, the AI's next task is to pinpoint the most likely spot along that line of response where the particle actually was. It analyzes all the signal data to zero in on that location.
To get even more precise, the AI also figures out the exact 3D point where each gamma ray hit the detector itself, including how deep it went. Knowing precisely where the signal landed helps sharpen the entire calculation of where it came from.
And finally, the AI cleans up the mess. It identifies and digitally removes the noise created by gamma rays that got scattered or bounced off course. What's left is a much, much cleaner dataset.
So after all that, after this complex AI-powered process, what's the bottom line? Why does this all matter for science and engineering? These trained AI models take the messy, noisy data that comes out of the real-world scanner, and they map it to a precise, high-resolution track of the particle's location. It's like turning a fuzzy, static-filled image into a sharp, crystal-clear picture. This kind of technological leap opens up entirely new possibilities. What new discoveries are waiting for us when we can finally see what was invisible, but now with near-perfect clarity? Imagine designing more efficient engines because you can watch the fuel mix in real time, or creating new medicines by seeing precisely how ingredients interact at a microscopic level. Having the ability to see inside the black box with this kind of clarity is going to revolutionize how we design everything. It really makes you wonder, what will we find next?